So, I hope everything is fine and think we can start the session. Good evening, everyone. My name is Syed Shabir Ahmed, and I am a research scholar and a Prime Minister's Research Fellow uh, in the Department of Applied Mechanics at IIT Madras. So, as you know, this course uh, is taken by Professor K. Ramesh. Uh, he happened to be in the faculty in the same department which I'm currently in, and the course is strength of materials, and these are like basic. These sessions are basically to help you with problem solving, like in addition to the assignment questions which you have to solve and give the answers. So this will help you to go through those assignment problems. Uh, we are not going to solve the same assignment problems which are given to you, but we will have similar kind of questions, or let's say those kind of questions which you will see in the uh, assignments. So if if there is any issue with the audio or anything, please let me know during the course of this meeting. And uh, so, as prescribed, there will this session will be held every week, Tuesday, 6 p.m. to 8 p.m. And I hope I will be able to help you with this problem solving regarding the course. And I hope you have watched the first week of lectures, uh, which have already been released. And I think the week two lectures have already also been released. And from that, I think if you have watched the videos, it would be easier for you. So make sure you watch the videos and attend the session so that you have uh, some idea to what to expect during the sessions. So, and that's it about me and everything else. So basically, I am working on my research is basically regarding digital twins or finite element model updating, and uh, the division which I am working in the department is solid mechanics. So the subject also deals somehow it forms the basic of my work also. So so I hope you have seen this assignment problems, and these are some problems which I have prepared today. So during this 2 hours of time, we'll try to solve these problems, and these are some questions. So let's uh, first, I think we can start with this problem, which is the question number 4. I'll just copy and paste this. So the problem is here identifying what are the beams which are present here, which are statically indeterminate. So can anyone tell me what is a statically indeterminate structure, or in this case, it's a beam. So, and what is a statically indeterminate beam or a structure? So, do you have any idea? Uh, because have you have watched the course, so can anyone answer? If anyone is willing to answer, you can switch on your mic and speak.
Indeterminate beams are the beams which in which the number of support reactions will be more than the number of static equations given.
Yeah, yeah, yeah. You are absolutely right. So in any beam, so because this is a 2D, these are all 2D structures. So for a 2D structure, we'll have three equilibrium equations, three static equilibrium equations. So those three equations are, first is sum of the horizontal forces are sigma fx equals to 0, and sum of the vertical forces, all vertical forces, sigma fy, in this case let's call it sigma fy is equals to 0, and sum of the moments should be equal to 0. So if all these conditions are satisfied, and we can say that the structure is in static equilibrium. So it means that structure is not moving when the load is applied. So static equilibrium. So this is for 2D. Uh, Suppose if we have a 3D structure, then we will have six number of equations, which is sigma fx is equals to 0, sigma fy equals to 0, sigma fz equals to 0. These are for forces, these three, and we will have sigma mx equal to 0, sigma my equals to 0, and sigma mz equal to 0. So we'll have total six equation in case of a 3D structure. So I don't think we'll be going to uh, see any 3D structures during the course. So for this case, this is the thing which we are going to use. So here you can see this first beam. We have uh, a horizontal reaction, a vertical reaction, and a moment. And here a vertical reaction and a horizontal reaction. So there are one, two, three, four, and five number of reactions present in this structure. So we have three equilibrium equations, and three equilibrium equations. If we solve these three equilibrium equations, we can only find out three number of unknowns. So here there are five. So it is not sufficient for the for this structure to only have static equilibrium equations. So that's why this structure is called as an indeterminate structure. So total number of reactions is 5, whereas the number of equilibrium equations is 3. So we need additional equations to solve this structure to find out the shear force, bending moment, or the deformation of the structure. So that's why it is called as a statically indeterminate beam. So the second one, can anyone tell me how many reaction forces are present for the B type of structure? This B, part B, this structure, this beam, B beam. So you can see the screen, and if you have a notes, you can just draw and let me know like how many reaction forces which you which can which are acting on this structure. If anybody has any answer. can turn on your mic. Okay, I think. Okay, I'll explain it. So here we have a roller support. So a roller support will give us only a vertical reaction, and we have a fixed support. So fixed support will have a horizontal, vertical, and a moment acting. And again here we have a horizontal, vertical, and a moment acting. So we'll have 3 plus 3 plus 1. So there are total number of unknowns or reaction forces is 7, and we have 3. So 7 minus 3. So we have static indeterminacy here, and we can give a number to the static indeterminacy. So number of reactions minus number of equilibrium equations, that is 7 minus 3. We can say that static indeterminacy of this structure is 4. Similarly, for this structure we have 1, 2, and a 3. This is a hinge, so that's why we have 2 reactions, and this is a roller, so we have 1, and this is a fixed support, so we have 3. So 3 plus 3 we have 6, but we have only 3 equations, so we have static indeterminacy 3 here. So all these 3 structures are statically indeterminate structures, or in this case beams. So I think there is a question in the assignment also, so you can look at it, and I hope this helps you to solve that problem. So okay, so the next question, I think we'll go with the first this question. Just so this is a structure, and here we have to find out the net reaction, moment, and force at the support here. So let's start with the first thing we have to do. So because this is a 2D structure, so we will have three, sorry, we'll have three equilibrium equations. So that is sigma fx equals to 0, and sigma fy equals to 0, and sigma m equals to 0. Or this is actually moment in z direction. So that's why we can you can say that sigma mz equals to 0, because let's say this is the plane of the structure which is there. So this is in xy plane. So if I apply any moment, let's say, and this moment will be in the axis which is inside the paper. So if you say this is the screen is the plane, uh, you can see this pencil. This is the z axis. So the structure will have moment to with respect to this axis. So this axis you can't see in the paper. It will be appearing to you as a point. So that's why this is actually this moment is moment about z axis. So that's why sigma mz equals to 0. So and here because we don't have any horizontal forces in the structure. You can simply remove this, or you can have it. Depends on the uh, sophistication or something which you want to have. So we can simply remove this because there aren't any vertical forces. So sorry, horizontal forces acting on the beam. So you can just simply say this is not required. So if there are any inclined load, if there is inclined load acting on the beam, or if there is any horizontal load acting on the beam, then we will require this. But if you use this also, you will get this. Let's say I'll just write the reactions which you can, which we have to derive here. So this is vertical reaction at A, and uh, or I think we can go with the course conventions. I'll say this as AY because this is acting in Y direction, and this is reaction at A, so I'll write it as AY, and this I can write it as AX. And so, and this moment I can write it as MA. Okay. So, and okay, so I'll take this moment direction as anti-clockwise. So, in this course, I think we all have this convention that we will take anti-clockwise moments as positive. So, I'll take MA in anti-clockwise direction. I'm just assuming it that the moment is in anti-clockwise direction. So, I think you all know the sign conventions. So, uh, this is the forces in the upward direction are positive, and along the positive x direction are positive, and moments are anti-clockwise is positive, and clockwise is negative. This is the convention, sign convention, which we are going to follow in this course. And so there may be different sign conventions followed by different authors in various books. So the thing is, we have to be consistent with the sign conventions uh, when we are when we are solving a problem. So I hope like you all are most of you are like basically undergraduate students starting out. So it is better for you to take a sign convention and follow it throughout the course, because uh, the course faculty or professor who is teaching you is taking these sign conventions. So it will be easier for you to follow them throughout the course so that you won't have any confusion when you are solving the problem. So if you are if you are using two sign conventions here and there, you will mess up and you will get wrong answers. So I think whatever uh, is being followed in the course, uh, I think you should follow that. So let's see. So I will start with this. So horizontal forces, we have sum of all the horizontal forces. So we have AX, and there is no other horizontal force acting on the body. So there are moments and there is a vertical load 20 kilonewton acting, and there are no other forces. So simply AX is equals to 0. So you can just I don't need to take this in the I don't need to take this equation. That's why I was saying I can neglect this. but if you want to take and you can write Ax equals to 0, that is also fine. Uh, and sum of all the vertical forces. So I have Ay vertical force uh, uh, and 20 kilonewton, which is acting downwards. That's why I'm taking it as negative. So Ay is acting upwards, as I have taken here. So upwards on the along the positive y-axis, and 20 kilonewton is acting towards the negative axis. So that's why I am taking Ay minus 20 summation of vertical forces. That's why I'll get the reaction as 20 kilonewton. So Ay I have got 20 kilonewton. So you can see another thing here. This is a simple cantilever structure, and there are only three reactions: Ax, Ay, and Ma. So this is a statically determinate beam. That's why we are going to get all these three reactions through these three static equilibrium equations. So, and the next thing we have is sigma mz equals to 0, means the all the moments should be equal, sum of all the moments should be equals to 0. So here we have Ma. So Ma I have taken anti-clockwise, that's why I'll take this as positive. And you can see minus 9.5 kilonewton meter is acting in the clockwise direction. So that's why I'll take this as negative. And I have again 6 kilonewton per meter, which is acting in the anti-clockwise direction. So I'll take this as positive, and I have minus, 12 kilonewton per meter, again acting in the clockwise direction. So I'll take this as negative. So I have minus 9.5 plus 6 minus 12. So Ma, we are going to get 15.5 kilonewton per meter. I hope you are doing this, and I hope I'm not doing anything wrong here. If there are any errors, please, if you notice any errors while I'm doing, please notice and let me know that this thing is wrong, or yeah, yeah, yeah. So is can anyone tell me that if this thing is correct or if this is wrong? I just want to know if you are attentive during the class. So if somebody has noticed something wrong, or if you think it is right, please switch on the mic and let me know. Like the reaction moment which I have derived here, at MA, is this correct or is this wrong?
So the
Wrong.
applied external
Hmm?
force should be considered.
Yeah, yeah,
The applied 20 Newton force should be considered.
yeah, yeah. You are right. So I have missed here this 20 kilonewton load. So we need to consider that also during our calculation. So this is the error here. So I'll just, I have missed this. So this 20 kilonewton load is also giving me a clockwise moment. So that's why I'll take 20 into 3 plus 3.5, which is like 6.5. Sorry, this is minus 12 minus 20 into 6.5. So now what will be our uh, answer? So we are going to get the reaction moment, I I think if you are using your calculators, or if you are very good with calculations, you can do on your own without relying on the calculator also. So I'm using a calculator here. So I'll get 145 kilonewton per meter. This is the moment which we are going to do. And this has to be in the direction which was given. So the moment is acting in the direction which in the anti-clockwise direction. So there is no change in the sign. So the direction which you have taken is correct. So if the reaction moment was acting in the opposite direction, this MA would yield me minus 145.5 kilonewton per meter. Since the from the calculation I have got positive, so there is no change in the direction in which the moment is acting. So the reaction moment is acting in anti-clockwise direction. So this is the uh, way in which we are going to get the reaction for a statically determinate beam. And I hope everything is clear. If you have any doubts, you can raise the doubt by switching on the mic, or you can also send the questions in the chat box. I think it's clear. So is it uh, is it clear? I'm assuming that okay. So someone is asking me why have we taken the moment in Z direction? So okay, so I'll just draw a 3D structure. Okay, so let's say this the same beam is we are looking at three uh, we are looking at like a 3D structure. So I'm seeing it from this angle. So this is the end of the beam, and this is the support of the beam. Okay, so now I'll take the so this is my x direction, this is my y direction, and this is my z direction. Okay, so okay, if I draw this here axis, this is z axis. Okay, this is z axis, and this is x axis, and the vertical one is the y axis. So if I apply any load, if I apply any moment or a load to this beam like this, so the beam will deform like this, right? So the beam is rotating about this z axis. Or let's say if I take this same thing in the 2D, so this is the cross section initially. After the beam has been deformed due to the applied load, the beam will rotate like this, right? So here you cannot see the z-axis, but here you can see the z-axis in the 3D. So this is the z-axis. If I am applying any load, this is the cross section is rotating about this z-axis. So that's why the moment here is taken in z direction. Okay. I hope this diagram is clear. Are you getting it, Sagar? Sagar Sahu. Uh, yeah. Just try to imagine it. My diagrams, I think, are not that good, but I'll try to improve during this during the course. Uh, this is the first time I'm using an iPad, so I think I'll try to improve. So I think you got it, like why we are taking the moment in z direction. So here you can't see it. So the z-axis in a 2D structure you can't see it. This is the point here. So the z-axis goes through this point. Okay. So and the beam bends in this direction. So it is bending around the z-axis. So that's why we take the moment as moment in z direction. So I think it is clear. If anyone else has any other doubt, please ask the question, or I'll go with the next question. Okay, so I think we'll go with this question. So second one, just copy this. So the question is here we have to get the uh, yeah. So here we have to find the shear force diagram and the bending moment diagram. So I hope you all know the concepts of shear force and bending moment, uh, and you might have watched the week one. So I'm directly going to uh, get this. So before trying to get the shear force or a bending moment diagram, so we have to uh, first get the reactions of the structure which are acting on it. So at the support. So there are here two supports, A, B. Uh, sorry, there are two supports, B and C. So we have to get the reactions at B and C. So here we have a roller support. So a roller support will give us two reactions. One is a horizontal reaction. Let's say I'm saying it as Bx, and there is a vertical reaction By, and there is a roller here at C. That's why I'm taking only a vertical reaction, which is Cy. So as I said, the load is acting in the vertical direction only, and this is a uniformly varying load. So we call it a uniformly varying load because it varies like linearly, and from here 0 to 20 kilonewton, varying uniformly, or you can say linearly varying load. That's why we have uh, we are saying this as a uniformly varying load or something, uh, some other terminology, like you can, I can say this also as a linearly varying. So before, as I said, there are three equilibrium equations: sigma fx equals to 0, sigma fy equals to 0, and sigma nz equals to 0. And because, as I said, only there is vertical load, I can directly write this Bx reaction as 0. I don't think I need to again write, because there is no horizontal load acting on the structure. So simply there is, I can do away with this equation. I can just not write, but I just want to show. That's why I'm taking this and writing Vx as 0. And there are three vertical loads which are acting. There is this By, reaction at B, and reaction at C, vertical reaction at C. And there is this uniformly varying load which is acting. So, well, this, because the load is acting in the downward direction, I'll we have to take this as a negative load. And there is a small correction here. This is not 20 kilonewton, and this is 20 kilonewton per meter. So this is because this is uh, distributed load. That's why I am taking it as 20 kilonewton per meter. So it is acting in negative y direction. That's why I'm taking it as negative, and I want to get the total load acting on this structure due to this uniformly varying load. I have to get the total area of this triangle. So if I get the total area of this triangle, I can get the total load acting on the beam. So that is, because this is a triangle. So area of a triangle, you can just write it as half into base. So this is the base. So base is 4 meters, let's say 4 meters, and the height of this triangle is 20 kilonewton per meter. So you can see this is the unit of this is meter, and this the unit of this is kilonewton meter. So if I multiply both of them, so I'll get kilonewton. So I'm getting the load instead of the uniform varying load. So you can say M and M will get cancelled, and you'll get the load. So if I do the calculations, I'll get Vy plus Cy minus 40 equals to 0. You can say By plus Cy equals to 40 kilonewton. So I'm just getting this equation. So I need to find out what is Py and what is Cy. So for that, I have to use this equation again, which is sigma mz equals to 0. So sigma mz equals to 0. So whenever we are going to take the moment, we have to take this about any point. So I am just taking this moment about this point B. So moment is acting in the Z direction, but I am taking sum of moments around this point B, and it has to be zero because this is a statically determinate B. So if I take sigma mz, this is the first equation. Okay, so sigma mz b equals to 0. We'll have uh, there is cy. So there is moment. I'll draw it again. So there is load acting like this, and there is cy and there is py. So because this py is going through this point B, I won't take this. There is the moment due to this is 0. So we have to take this distance is 4 meters, and there is no other load acting on the structure. So I'll take cy, which is acting in anti-clockwise direction. So cy into 4 moment due to this will go like this. So it is acting in upward direction, and the distance is 4. So that's why I'll take cy into 4. And this is the load, uniformly varying load, and due to the moment will be total load into centroid of this triangle. So centroid of this triangle lies here at this point, okay, at the midpoint only. So half into 4 into 20. This is the load, and this is the centroid of the triangle. So the total load will act at the centroid. So this is at centroid is at a distance of 2 meters from the point B. So if I get this, I'll get Cy as 20 kilonewton. So I have got Cy from this equation. So the next thing we have to find out is what is By. So if I take this second equation and I substitute Cy in the first equation, you will get again By is equals to 20 kilometer. So these are all the three reactions which we have to find out. So Bx is 0, By equals to 20 kilometer, and Cy equals to 20 kilometer. So I hope up to this part there are no doubts. If there are doubts, please let me know. So I assume everyone has got the hang of finding out the reaction forces using the static equilibrium equation. So the next thing is first we will go and find out what is the shear force diagram. So for that, uh, I'll again draw this field. This is Cy, this is Cy, and this is the load. So I am assuming this midpoint as D. Sorry, we already have D, so I am assuming this as E. So midpoint of B and C, or the point at which maximum intensity of the UVL occurs. So this is point E. So while doing the calculations for shear force and bending moment, so we'll do it section wise. Whenever there is a load acting at a point, uh, or if there is any, uh, let's say, uh, or a couple acting at that point, so we have to divide this into sections, and then we have to find out the variation of shear force and bending moment. Here we will find out the variation, let's say first in AB, section AB, and then we will go to section BE, and then we will go to section EC, and then we will go to section CD. This is because there will be jumps occurring in the shear force diagram or at the point where there is load acting, and there will be jump occurring in the bending moment diagram at a point where there is moment acting. So in order to take account of that, first we have to take a section uh, in the segment where there is no variation. So if there is a from A to B, there is no load acting. So I can take a section here and I can find out the shear force and moment diagram. Whenever you come to B, there is a load acting here due to the reaction. So there will be change in the shear force diagram. So that's why you have to take again a section here between B and E. So from B and E, there is a variation from 0 to 20 kilonewton. So this is one kind of variation. So you have to take a section here. Again, E to C, there is a variation of 20 to 0. Again, you have to take a section like this. We have to divide this into segments, and we have to do the shear force and bending moment. So let's say I think let's say first we will take the section AB. So first I'll go with all the shear force calculations. Okay, so in shear force variation in AB. So in AB, if I take a section here, I'm just cutting a section. So from A, this is the section I have cut. Okay, so there are no forces acting here, and there is no reaction at point A. So the shear force in this segment, shear force in this segment AB will be entirely zero. So again, so and similarly in shear force in CD. So in CD also, if I take a section like this here, and I take this part D, and I have cut a section here. So X. Just taking this section as X. So there is no load acting and there is no reaction. So that's why here also shear force is zero. In this part also it is zero. So now we are going to do the hardest part, which is shear force variation in the section BE. So for that, I have to take a section here. So I'm taking a section here, and let's say this is at a distance of x from point B. So this section is at a distance of x from point B. So shear force variation in BE. So if I draw like this, and this is A, this is B, and the section which I have cut at some distance x, and this is the load at some point x. So now I have to find out the shear force. So here, whenever we are trying to get the shear force or bending moment, so we generally follow a sign convention. I think you have watched the lectures, and professor has given you the sign conventions. So uh, I'll just explain the sign conventions which we are going to use. So let's say you have a beam. Let's just a simply supported beam. Just a simply supported. Like this. So the thing is, we are taking this as positive x-axis, and we are taking this as upper direction as positive y-axis. And so if I cut a section here, this is the part which I'm going to get. So I'll assume there is a reaction at the hinge. So every time we assume that the reaction we are taking in the positive directions. That's why we will take it as positive, upwards, and in the positive x direction. Anytime we are going to use this, like we'll take the reaction. We'll assume it. If there is a change in the sign convention, you have to after getting the reaction, if this is negative, the direction is opposite to what you have assumed. So because I am cutting the section here, this is positive phase, because from here to here I am going in the positive x direction, and I am cutting the uh, section here. This is positive phase. That's why I am getting, I'll take reactions here in shear force and bending moment. Also in the, I'll assume them as positive, acting them in, I'll assume they are acting in the positive x direction, positive direction. So that is shear force is generally assumed as V. So in this course, I think we are using this symbol for shear force, and the bending moment we will assume is acting. Bending moment at point x will act is acting in the anti-clockwise direction, because we have assumed that uh, we have taken the sign conventions that upward forces are positive and anti-clockwise moment are positive. I am taking uh, this sign convention here. So suppose if I take uh, the section again like this, like this. So now before this I have taken this section, and now I am taking this section. So I have cut the beam into two parts. Okay, so I have taken the section and cut the beam into two parts. So this is a roller support, and because from here I am going in the negative x direction and cutting the section, this is called as negative phase. So that's why That's why we are going to use this. The reaction, I am assuming it is acting uh, BC, right? So in upward direction, that is positive. Because when we are going in negative side, we are going to assume that shear force, because this is negative phase, and we are going to assume that shear force is acting in the negative direction, and the bending moment is also acting in the clockwise direction. So we are going to assume like this. Uh, this is negative phase, and we are going to take the shear force and bending moment in the negative directions. So negative is like positive. You can just say it like that. So because I have cut the section, so if I join both of them, if I join both of these sections, this upward force and this downward shear force, both are at same point, so they should cancel out each other. Otherwise, there if the shear force is not balancing when we join the sections together, it means that beam is going to fail. It cracks. So they have to both balance each other. So that's why we are going to take convention like this. So this is acting in negative anti-clockwise direction, and this is acting in clockwise direction. So that's why the bending moment will both these value will be same. So clockwise and anti-clockwise have to cancel each other, and that's have to cancel each other. That's otherwise there is the beam is not in static uh, equilibrium. So I think you have understood the sign convention. If you have any doubts, please ask me now itself. Because this is very important. Sign convention while doing the uh, while doing shear force and bending moment diagrams is very important. Of course, you can use different sign conventions if you want, but the thing is you have to be, as I said, you have to be consistent throughout while you are doing a particular problem. If you are changing the sign convention midway, then all the answers which you get will be wrong. So take this as a warning or a caution, whatever you want to say, and use this sign convention. So somebody might have a question. I think this is properly explained during the lectures, because I don't know if you have watched. That's why I'm explaining it again. Uh, if you have again doubt regarding this, there is more elaborate explanation. You can go and watch. Just go and search engineering mechanics, Professor K. Ramesh. So there are NPTEL videos available on YouTube. Engineering mechanics. In that there is a lecture about beams. I think uh, a lecture, first or second lecture. There you can find a more elaborate explanation regarding this. So there, professor has given a very nice explanation why we are taking. I think I have clearly explained it to you. Uh, so this is the positive. This is the positive phase. That's why positive phase. This is the positive phase. That's why I'm taking reaction, shear force and bending moment also, assuming shear force and bending moment also acting in the positive direction. And this is the negative phase. That's why I'm taking shear force and bending moment also acting are also assumed to be acting in the negative direction. Just say that, just remember like negative and a negative will give you a positive. So, and the thing is, when you join these two sections, shear force at the left of the section and shear force at the right of the section should add up and give you 0, and bending moment at the left of the section and bending moment of the right of the section should add up and give you 0. So I think this is clear. This has been established properly. If you have any doubts, please again ask uh, in the chat box, or you can turn on your mic. So, so I'm just going to erase this part. Okay. So in this problem, I have cut the section here, and that's why because I'm coming in positive x-axis direction, I'm cutting the section here. That's why this is the positive phase, and in the positive phase, I'll take shear force Ex and bending moment as mx. So I'm just going to calculate the shear force. I think that's why bending moment at x. So these are the directions which I'm taking. Okay. So so what is shear force? So shear force at any section is sum of all the forces, acting on the structure till the section which we have cut. So till x, what are some of all the forces acting? That is called shear force. So here, in order to get shear force, we have to take sigma fx equals to 0 for this cut section. So we have only Vy here, and we have Vx also acting in upward direction. That should be equal to 0. In addition to this, there is also this load. So this is at a distance x. So the thing is, I don't know what is the intensity of the load at distance x. For this, I am going to use the concept of similar triangles. I hope you know what is the concept. You during your grade 9 or grade 10, you might have got introduced to this concept. So I have cut this section here. So so this is x, okay, and this is 4 meters. So using this principle of similar triangles, I can write 20 by 4 equals to, let's say, uh, the load at let's say whatever you want to. I'll just write as uh, what you can say, x uh, px, okay, or just load acting at uh, load intensity at x. So px by x. So if I do this, I'll get px equals to 4. This is, sorry, this is 2 meters till the point T. So 20 by 2. So 10 into x. So you get px as 10 into x. Is it clear to all of you how I have taken this? This is the load intensity at x distance from the point B. So this is point B and this is point B. So using the concept of principal triangles, we are going to get this. So I have got the intensity now, which is So this is 10x. So now I can get the total load, which is half into, because this is the load is acting in a negative direction, and say half into base is x, half into x into 10x. So you can get by we have, which we have already calculated, is 20 kilonewton plus Vx minus 5x square. So if you take this, Vx equals to 5x square minus 20 kilonewton. Is this clear? I think should be clear, otherwise you can ask me. So this is the shear force variation in the section, in the segment BE. So 5x square minus 20. So let's say if you want to, from B to E, this is the shear force variation. Let's say if you want to calculate what you can say, shear force, what is the shear force at E? So shear force at point E should be equals to, because it is at a distance of 2 meters from point B, I'll just substitute x equals to 2, and I can get 5 into 4, 20 minus 20, though. So the shear force at this point is 0. So I hope you have got this. So this is the shear force at point E. Shear force at point E. Okay. Next, we are going to see the section or the segment EC. So in the segment EC, I am just going to take this section like this. So see, this is some at a distance. I have taken a section which is at a x distance, and this is t. So here also the thing is, I can take this section like this from point C, or I can take this section like this also. A, sorry, this is B, this is A, and this is E, and this is E. So if I join both of them, they have to, they are same. So the scaling is not correct, but okay. So I have cut the beam into two parts. So you can take the section like this also, you can take the section like this also. But the thing is, while if I take the positive positive face like this, I'll get extra calculations, because this is not a triangle. Uh, uh, you have to face like you have to get the uh, calculations, like you will get lengthy calculations. If I take this, there is simply a triangle. So in order to avoid the complexity, I'll just take this part. So I'll just remove this left side. I have cut this into two parts, and I'm just taking the right side part. Okay. So as I have said, this is negative phase. So we'll have shear force. We'll have shear force in the. We'll assume that shear force is negative and shear force is in the negative y direction, and the moment is clockwise. Bending moment is clockwise at this section. So after doing this, the same thing, I'll get the intensity here again as 10x using the similar triangles. Same thing. This is E. This is C. This is 20 and this is 10x. From the distance, this is the intensity. So the intensity is 20 kilonewton per meter here at point E, and in between at a point at a distance x, the intensity is 10x. You can just like at if you take point C, the distance from point C to point C is 0. So you can just say x is equals to 0. Here load intensity is 0. I'm just trying to cross check here. So if you want to get the load intensity at point T, you can just put x is equals to 2 because it is at a distance of 2 meters from point C. 10 into 2, 20. So this is 20. So the uh, variation of this load intensity is 10x. So I think you have got this. Yeah. Do you have any doubts? Not, we'll continue. Okay. So again I am going to take sigma Fy equals to 0, and again like this, I know I am taking Cy, taking this is Cy. Cy is acting upwards and there is Vx acting in the downward direction, and there is half into 10x into x. So if I substitute Cy is 20 again, so I'll get 20 minus 5x square, which is the shear force at the section X. So this is the shear force variation in the shear force variation which we have got in the section C and E. So if I put if I want to calculate the shear force at point T, shear force at point T, I'll just substitute 20 minus 2, which because it is at a distance. Again, I'll get shear force at T equals to 0. So the thing is, either you take in the at any point on the beam, shear force should be same. So there can be a jump. So if there is a load, like a point load, there can be a jump. Let's say. So I have got these two variations. Okay. So shear force at uh, this point is shear force at E is 0. So now I'll draw the shear force diagram. So the shear force diagram for this structure A, B, C A, B, C, D, E. So I'll just take like this. Shear force is at point E, shear force is 0, and it is varying like this at 0. And again, from here to here, this will go like this. So this is the shear force variation. Okay, you got this. I hope you got this. Shear force is 20, 20, 20, 20, 20. This is the shear force diagram, or you can abbreviate it as SFP. Okay, who is okay? Uh, one doubt from one of the problems solved during the lecture. So, Priyanka, I haven't seen. Can you let me know in which lecture is that problem explained? I'll just complete this problem and again I'll get back to I'll get back to your doubt. Okay.
Yes,
So
sir.
you just till then you just find out the lecture which the problem is in which lecture the problem is there. I'll just let me know in the chat box which lecture. I'll just see and answer your doubt. You also write.
Okay, sir.
Yeah. So so this is the shear force diagram which we are getting. So from here to here shear force is 0, and again it is after that it is 20 kilonewton at point B. Again it comes to 0 at point E, and from E to C again it goes from 0 to 20 kilonewton, and again CD it is 0. So I think this is pretty clear how to get the shear force. So now coming to the bending moment, simply again as I have explained, I think I don't need to calculate between segment A, B and BC, because there if I take a section there are no loads acting, no forces act, no reactions present. So the bending moment in that part will be 0. So we don't need to do that again. So instead of that, I think we can just go for sections BE. So from the section BE, again I'll just PMD. So here bending moment variation in BE. So in BE, if I take let's say, as I said, this is 10x. I'm taking a distance of x from point P. This is. So what is bending moment? Bending moment is nothing but sum of all the. I'll just write the sign conventions. So bending moment is sum of all the moments acting on the structure till that section. So till the section X, what are all the moments occurring in our structure? That is the bending moment. So if I take bending moment, for bending moment, I simply have to take let's just take uh, sum of all the moments in z direction at point x equals to 0. So I am calculating moment about this point x. So I don't need to take Vx because it is passing through the point x. So basically I have dy which is acting in anti-clockwise direction at a distance of x, and I have uh, what due to this load half into 10x the area of the triangle will give you the total load, and this is acting at a distance of from x. This is acting at a distance of one third of x. The centroid is present at a distance of one third of x. I think you know this. From this side, this is one third. The centroid is present at one third of the distance, and if I come from this side, it is at a distance of two third. Okay. So because I'm taking moment about this point x, so I'm just taking one third of x. So this is the moment due to the load, and this is this is sorry, and clockwise direction. The moment due to the, and I have moment due to bending moment at this point is Vmx equals to 0. So if I do this calculation, we are going to get Vy into x. I'm just taking everything on this side. So negatives will become positive. 5x square x cube by 3 is the bending moment at x. So dy is 20x. Okay. So this is positive because this is the moment is acting in the anti-clockwise direction due to the load. That's why we have this positive. So positive become negative here. So 20x minus 5x cube by 3. So this is the bending moment at section x. So if I want bending moment at point E, so bending moment at point E will be, so simply if I have to substitute 2 here because 2 is present at a distance of 2, E is present at a distance of 2 meters from point P. I'll get 40 minus 40 minus 40 by 3. So which is simply 80 by 3 kilometer per meter. So this is the bending moment at point P. So if I want bending moment at point B, so bending moment at point B will be, I'll just put, I have to put 0 because x is 0. So bending moment at point B will be 0. So similarly, you can get the bending moment diagram, bending moment variation in EC. So same thing, again you have to go through. So this is distance x and this is C and this is D. So if I, same thing here, the As I have said, we are taking negative directions clockwise. Bending moment will take clockwise. And so if I take the moments, bending moment at x, because this is clockwise, and about moment about x I am taking. So this is clockwise, and this is due to the load also. We have half into 10x into x into, again this is acting at a distance of 1/3 from the face of the triangle, and due to the reaction we are going to get cy into x, because this is acting in an anti-clockwise direction. So cy into x. So if you do this, going to do this, we are going to do this again, bending moment at x in the section CE will be 20x minus okay, okay, yeah, 20x minus 20, the same thing, 5x by 5x cube. So if I substitute x equals to 2 here, in order to get the bending moment at t, substitute x equals to 2, again I get 8 over 3. And if you want to get bending moment at c, you just have to substitute x equals to 0, again you get 0. So now I can draw the bending moment diagram. A, B, C, D, and this is C. So bending moment at C and also E, just so this is 0 at this point, and this will come like this, maximum at this point, and come like this. So this is what the bending moment diagram will look like. So bending moment is maximum at point T, which is 83 kilometer meters. So shear force is maximum at point B and C. So here it is 0, and here it is 20 kilometer, 20 kilometer. So at supports the bending moment is 0, and at the point uh, at the point T, bending moment is maximum. So that's how we are going to get the shear force and bending moment diagrams. I think we are clear here. If you have any doubts, you can ask me. You can ask. Otherwise, we are going to move forward with the next lecture. next question. So, are we clear? I hope I have satisfied this discussion. If you have any doubts, please let me know. Okay, I'm just cross checking this diagram. Okay. Yeah. Slide change. Diagram will look like this. So this is the bending moment diagram. Okay. Think I think you are getting an idea how to solve this problem. And think think you all would have gone through the engineering mechanics course and uh, calculated uh, uh, trust problems. I think you have done the trust problems. If anybody has no idea how to solve a trust problem, please you can tell me. I can I can just show you once. Okay, I'll just give an idea. You can do this because I'll tell you how to take the sign convention. Here also this part comes in. Where you have to take the sign convention. So so in the trust problem also, if you want to find okay okay. So in the trust problem also we want to find what are the member forces acting in the truss. So let's say this is A, this is joint 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 F, and this is joint G. So there is a load acting here. There is a load acting at point G, at joint G. So these are all the joints. So whatever I am highlighting, red dotted thing, these are all the joints which are joining the truss members. So this is a, let's say this is one member, this is one member. All these members, slender members, are joined together to form a truss. So we will assume that truss members will have only axial reactions. So in general, in real life, there will be bending moment, shear force also in the truss members. But to simplify our discussion, we will just assume that uh, we have only uh, uh, we have only this thing that tension and compression. We will assume that truss members are only able to handle tension and compression. Okay. So any problem beam, either it is beam or also either it is like uh, truss. First, we have to find out the reaction forces. So here there is AX, there is AY because this is a hinge, and because and also there is BX and there is BY. So there are four reactions which you have to find out. Okay. So simply you can just use the equilibrium equations. Sigma Fx equals to 0, sigma Fy equals to 0, and sigma m. At let's say I'll just use this point sigma mz about point uh, A. So just point A equals to 0. So if I do this, I can get, let's say if I take sigma here Ax plus Bx equals to 0. Sigma Fx equals to 0 if I take, this will be the thing which I made. And sigma Fy equals to 0, if I take, I'll get Vy plus Ay equals to 0. And we can also have this moment equilibrium equation about, if I am taking about point A, I will not get
Sir,
yeah.
uh, for y direction, it will not be 0, no, sir. It will be p, no, sir.
Oh yeah, sorry. Only in the x direction it is 0. And if I take moment about this point, so the force By passes through this point, the force Ay passes through this point, the force Ax passes through this point. So I won't get moment about this. I won't get any moments due to this. So that's why due to that forces about this point. So we'll only have Dx which is acting in anti-clockwise direction, Dx which is at a distance of 1 meter, and there is P which is acting in the clockwise direction, which is at a distance of 3 meters from X. So simply I'll get Vx equals to 3P. I'll just check once. I think similarly, if you substitute Vx, yeah, Vx equals to Vx plus Ax equals 0. So if I substitute Ax, I'll get minus 3P. Okay. So the reactions, I think the reactions AX and VX, simply I think we can go from this point. We have got, sorry, AX and VX. So BY and AY, and yeah, you can take another moment, you can calculate about any point, or simply by calculating the members forces from starting from point G. If I go like this, so I think we can you will be able to get it. So first, in the trust problem, there are two ways to solve a trust problem to find the member forces. So one way is to uh, one first method is called method of joints, and the second method is called as method of sections. So method of sections is useful when you only have to find out the member forces in some members. Let's say the examiner has asked you to find out the reaction for member forces in DE, or only DE, DF, or C, something like that. Only then you can cut a section and you can do the method of sections. But here, this is a little bit, this is not a simple, straightforward problem. I think I won't explain it today, because you need to again go from here to here. There is a lot of, I think we are left with only 10 minutes of time. I'll just give you the thing. So if you take the point G, I'll just give you the, uh, there is a load acting. So uh, this is force acting in the member FG, and sorry, acting due to the member FG, and this is the force acting due to the member EG. So in this way, I am just assuming that the force is acting away from the joint. So this is just an assumption. Again, this is a sign convention. However you want to uh, use the sign convention, it depends on your choice, and you have total freedom. But in this course, I think sir has taken this sign convention, always taking away from the joint. And at this point, you have to take sigma fx equals to 0 and sigma fy equals to 0. So if you take this sigma fx equals to 0 and sigma fy equals to 0, here this is, as I told, we only have uh, member forces like tension and compression, and we don't have any bending moment or something here. That's why we will only have two equilibrium equations, sigma fx and sigma fy equals to 0. So if you take at this point sigma fx and sigma fy equals to 0, you can easily get force acting in the member Fg, and you can get force acting in the member Eg. So if you get this forces as positive, it means that the trusses are having tensile, the trusses are experiencing uh, tensile load. So if you get it negative, it means that the truss member is having compressive load. So see, if you have got this, then again you can go to this F uh, point F, and again you can get take a method of again you can take the joint F. Again, this is force in the Fg, and again this is the force in the member Fe, and this is force in the member Pf. So again, you can take equilibrium equations here. You know this, you don't know do these two. You can calculate using the equilibrium equations. So from this you can go to point E, then you can go to point D, like this. Then you can go to point C, then you can go to point this point. You can get the reaction AX, then you can get to point B. You can get the reaction sorry, AY and BY. So like this way, you can go from point one joint to say second, from one joint to other point. Take equilibrium, uh, take equilibrium equations at each joint, and you can calculate all the member forces. So this is the way how you do a truss problem. So I have just given a summary. You can just solve some problem from any book or lecture. I think uh, that would be good. So someone has asked, what is the uh, in week 3? So I'm just going to check what is that question.
Sir,
Yeah,
may I ask the question, sir?
yeah.
Sir, in that week 3, sir, lecture,
Yeah,
sir had solved a statically indeterminate problem, bolt and nut problem.
yeah. Okay,
In that, he had taken the total deformation as delta sleeve plus
Flat
delta
10%
bolt.
off on
okay,
But
okay.
in that sleeve is getting contracted and the bolt is getting expanded. Why did he not take the sign differently?
Oh, I'll just check that one.
Yes.
by delta by L, and this is famous. So when it is rigid, you must have observed that y and done wheel. Once I have cos theta and put the limits, I get the elongation of this. What is the size of colors? And nature is also very nice. In the case of B, plain information, my understanding have taken, because you skate. So this is again straightforward.
Stress component is scalar. That is the lecture, right? Yeah.
Yes, sir. At 28
Uh,
minutes, I think the lecture that part starts.
28 minutes. Okay.
Sleeve is deformable means when I rotate it,
So
the nut would have
what is your
moved
doubt
down.
here?
Fine. So we will visualize that. So it
So while
would have
solving
moved down,
this
and
statically
the
indeterminate
complete
problem, he said
deformation
we
will
should
now
take
be
geometric compatibility as delta is equal to delta
borne by the
sleeve
sleeve.
plus delta
That's
bolt.
also acceptable.
Hmm.
But in
And
reality,
professor also told
bolt
that
is also
visualize
deformable,
that sleeve is getting
sleeve is also deformable. So what
contracted
happens
and
is
the
while
bolt
you
is
are
getting
tightening
expanded.
it,
Okay.
the
So he
sleeve is
took
getting
total deformation
compressed
as both
and
plus
bolt
with
is
plus
also
signs.
getting
Why?
elongated simultaneously.
Okay.
So to internal pressure. I have shown in old detail, but I have shown all that. Don't make a, please make stress. If you actually solve this, 1 plus delta 2. See, this
Okay. One concept. Okay. Yeah, I haven't watched this lecture. I think I can't watch it right now. So
Next week,
Yeah, you can just mail me. Uh,
or it's a
just
next
mail.
week session, or like it will be there now. So next week also same time.
Yeah, yeah. Or if you want, I'll just check today and I'll let you know. This is my mail ID. You can just drop a message here.
Okay, sir.
Yeah, so I'll let you know.
So one more doubt, sir, I have.
Yeah,
Sir, regarding like this is regarding free body diagram, sir, for beam.
yeah, yeah.
Like if I take a propped cantilever beam
Hmm.
with the internal hinge, sir.
Internet hinge.
Yes, and
Hmm.
a concentrated load is acting on the internal hinge.
Hmm.
So, like, if I want to find the force, and if I take like two free body diagrams, like I have the doubt on, like whether I should consider load P on both free body diagrams or only one.
The thing is, you can consider it on one, or you can consider half load on each part.
Okay. Either
Yeah.
like it will be P by 2 on like fixed free body diagram
Uh,
and P by 2 on the simply supported.
yeah.
Or else P on fixed and 0 on the simply supported.
Yeah. You can do it both ways.
Okay, sir.
Yeah.
And last doubt, sir.
Yeah.
Like while solving like some other statical indeterminate problems, sir, like steel reinforced concrete beam, like that bar problem, sir.
Okay.
Like in that, like we while solving, like we do the force equilibrium, no, sir. Like F is equal to uh,
Hmm.
F, like we will equate the force. Similarly, can we like equate stress also?
I didn't understand your question.
Like
Stress.
if like in steel, if there is a steel reinforced concrete problem, then we
Hmm.
take the total force is equal to force on concrete plus force on steel.
Yeah, yeah. Hmm.
Can I also take it as total stress is equal to stress on concrete and stress on steel?
No, no, no. Stress is different. Uh, Stress is actually distributed, right? You cannot take. You can only you can take sum of forces. Stress is not that straightforward. You cannot sum it. Stress.
Okay, sir. So like if I have to solve problem, then I have to take force itself.
Yeah.
Like
You
force,
cannot.
like from one part it gets transmitted to other part. I can't do the same with stress.
No, no.
Okay, sir.
Stress can be different actually.
Okay, sir.
Yeah. It at the interface stresses can be different. So you have to be careful.
Okay, sir.
Yeah. So total load is load shared by the steel, load shared by plus load shared by the concrete. So for stress you can't do that.
Okay, sir.
Yeah.
Thank you, sir.
And other questions I think uh, you all can do them. These are basically compatibility problems like a rigid board. This fifth question I'll just explain how you are going to do it. So uh, because uh, this load is applying this load is being 200 kilonewton load is applied on this bar. So we have three supports of let's say steel uh, wire, aluminum wire, and copper wire. So because these are parallel, like these are acting like parallel springs, so the deformation will be same in all the springs. So you can take deformation at all the springs equals to the deformation in all the springs as same, and you can solve this problem. So I think you have this. First, you can take, let's say, deformation in steel wire equals to deformation in aluminum wire. From that, you can get some uh, uh, some relation, and again, you can get deformation in aluminum equals to copper. From that you can take another relation, and sum of all the loads experienced by this steel, aluminum, and copper wires should be equals to 200 kilonewton. So P steel plus P aluminum plus P copper equals to 200 kilonewton. So from that you get the loads, and uh, from these two equations, compatibility equations. First one is the compatibility equation, and again using the equilibrium equation, you get the loads, and after that you know the area here. Area is given, so if you know the load and area, you can get the stress in each one. So this is a this is also a statically indeterminate problem. So I think uh, you can solve this problem. So this is also a simple problem. You can solve this. You just have to find out the distance uh, at which reflection in both the strings should be set. Okay, so since I have not solved this problem completely, trust problem, I think if uh, I have the time, I I can solve this in next week, because this will take a lot of time from going from joint A, joint B, joint C, all this stuff. You can go it easily. So the thing is, you should have take any joint such that there are only two unknowns. So because we have only two unknowns, first we have to take this joint. There are two unknowns, member force in this and in this. There are two unknowns. You solve using the equilibrium equations. You get two, and again you go here, you go here, you go here. By doing this, you can get the member forces. So always assume that forces are acting away from the joint. If you get the force as positive, that means the member is experiencing tension. If you get the force as negative, that means the member is experiencing compression. So that is the way. So going from one joint, one joint, one joint. So you can solve this. So I think uh, everything is fine. So if anybody has still any questions, you can ask. Yeah. I if you have any feedback, you can let me know right now. So like you want some more detailed explanation, or if my presentation is not good, I'll try to improve in the next session. So you are free to give me any feedback. I also want to improve. So if you have anything uh, which is not comfortable to you during this session, you can let me know, please. So, so I might have messed up a little bit. So my handwriting is also not that appealing, let's say. So I'll try to improve. So if you have any feedback, you can write it in the chat box that you want some more explanation or some different kind of problems, or something else, whatever you have felt. So, nobody has anything to say. Okay. So I have you understood whatever has been discussed today? Can anyone give me the answer, chat box or something?
I missed the first half, sir, but I joined like in the later half.
Ah,
I understood, sir, the concepts what you taught.
okay, okay. Okay, so I think we'll wind up the session today. So again, we'll meet again on Tuesday. So thank you all for joining. So whoever has joined, so we'll meet you in the next session. So yeah,
Thank you, sir.
Thank you, sir.
yeah, thanks. Thanks. See you.